Hi everyone, welcome back. In this lecture we're going to continue our development of graph theory and we're going to look at Eulerian trails and circuits. So here's a motivating problem. In fact, it could be argued that this is the problem that gave rise to graph theory. So we have a city of Königsberg and this city has 7 bridges. Now the city has 4 land masses that are connected by these bridges. And the underlying question is, can an inhabitant of the city go out for an evening stroll, leave their home, cross each of the 7 bridges exactly once, and return back to their home? Be a nice evening stroll. Is such a stroll possible? So that's our question. Is it possible to walk around the city, cross each bridge exactly once, and return to where you started? So if we just sort of fiddle around with this a little bit, maybe we live over here and I can cross a bridge, maybe cross another bridge and another one and another one. Maybe I'll cross this one. The problem is now I'm on a part of the city where I can't cross a new bridge to get back. So I'm stuck. So maybe I just made a poor choice. Maybe I'll wander around here and I'll walk across this one. Okay, now I'm at least on the same piece of land that my home is on, but I still have more bridges to cross, so I could cross this one and cross this one. Oh, and now I'm stuck again. There's no new bridge to cross. And so that's the question. Maybe I just made a couple of poor choices. Maybe you can fiddle around with this a little bit and see if you can find a stroll. What we've got drawn over here is just an abstraction of the essential properties of this map on the left. Each of the land masses is just denoted by a vertex. So those are the 4 land masses. Each of the bridges are denoted by those edges. So for example, this could be bridge 1, bridge 2, and bridge 4. This was bridge 3, bridge 7, bridge 6, and bridge 5. And those vertices are representing these land masses. So we've got an abstract representation of this problem using a graph. And so that's where graph theory comes in. And so the question really is can I find a walk around this graph that starts at a vertex, ends at a vertex, and doesn't use any edge more than once, but because I want to cross every bridge, it needs to use every edge exactly once. That's going to be the main problem we're going to be looking at in this lecture. So let's have a look at a definition. An Euler circuit, or often referred to as an Eulerian circuit, Euler circuit of a multigraph which has at least one edge, is a circuit, here I've called it W, and a circuit consists of vertex followed by an edge, then a vertex followed by an edge, and so on, such that every edge in E, so every edge of the graph, appears once in this circuit W. So E1, E2, all the way up to En, those are going to be all of the edges in the graph, and they're going to be used exactly once. Notice we're starting at vertex V1, we're ending at vertex V1. So that's why it's a circuit. We're starting where we end. So the question of this previous problem about can I find a way to wander around the city and cross each bridge exactly once is really a question as to whether this graph has an Euler circuit. Does that graph have an Euler circuit? So let's explore a little bit about Euler circuits right now. We'll start with another example of a graph, maybe a graph that looks like this. Here's our vertices, and the edges I'll draw in. Maybe these are our edges here. And so that was maybe vertex 1, vertex 2, 3, 4, and 5. Does this graph have an Euler circuit? So is there a circuit on this graph that uses every edge exactly once? Let's see if we can find one. So we might as well just start at vertex 1 and see what we can do. So we use that edge once, we'll go to vertex 2, then we'll use this edge, then we'll go around these parallel edges. Then we'll use this edge. Then we'll go around the loop. And then we'll come back to where we started. And so yes, it does have an Euler circuit. We can jot that one down. So here's our Euler circuit that we just found. And I'll just list it in terms of the vertices. We started at 1, we went to vertex 2, then to vertex 3, then to vertex 4, and back to vertex 3. Of course, at this point, just listing the vertex, that's a little bit ambiguous because I just said I went from vertex 3 to vertex 4. There's really two ways to do that. I could have used this upper edge or this lower edge. But then I come back from vertex 4 to vertex 3. So it doesn't matter if I went like that, or I went like this and like this. So even though there's a bit of ambiguity as to which edge was used, it doesn't make any difference here. We're just interested in the existence of an Euler circuit, and this list actually encodes two different ones. One where I use the upper edge to go out and the lower one to come back, and vice versa. The upper edge, or the lower edge to go out and the upper edge to come back. So now I'm at vertex 3. I go to vertex 5 and then vertex 1. If you're still troubled by this, me just listing the vertices and not the edges, well, you could do that as well. We just have to label all the edges, and then we could list the edges in between, and that's certainly fine. But I just wanted to avoid having to do the extra work of labeling. So we've got our Euler circuit. So there's an example of a graph that has an Euler circuit. Now I got a question. What do we notice about the vertices in this graph? What do we notice about the vertices in this graph? Okay, what do I mean by that? Well, there's many things to notice, perhaps. So we have an Euler circuit in this graph. I would like to try to figure out conditions on when Euler circuits exist versus when they don't exist. So a part of that is looking at a graph that has an Euler circuit, like the one we have here, and trying to just get from it properties that the graph has. So in this case, I'm asking specifically about the vertices. Do we notice any properties that the vertices have? One possible answer could be, yeah, every vertex, well, I had to go in it along an edge and then leave it along an edge. And some of them I went in, like vertex 3, I came in along one edge, left along another edge, then came back in along an edge and left along another edge. And so that's telling me that, hey, wait a minute, every vertex has even degree. If there's an Euler circuit, then every vertex should have even degree. And that's what I'm just going to make the observation here. In fact, I'll make this observation a little bit more formal. So here's our observation. If, well, I'll write it this way. G has an Euler circuit. That implies every vertex has even degree. That's just an observation we have from this one example. Okay, so it might not be true. It might just be a consequence of this one example that it just happens to be the case. Why is it true in general? But as I said, if we think about this a little bit more carefully, what's happening here when I've got an Euler circuit is for any vertex, maybe I'll look at vertex 5, I've got to come in along an edge. If I'm going to leave, I leave along an edge. But then if I come back in again, then I have to leave again. So every time I come into a vertex, I'm going to have to leave that vertex, which is a count of 2 to the degree. So the degree has got to be a multiple of 2. You might say, well, what about vertex 1? I didn't leave immediately as soon as I came into it, or vice versa. Well, the idea is with vertex 1, that was our starting vertex. So we left, and then eventually we came back to it because we had to end where we started. So again, it had to have even degree. I could add some more edges to the graph. So for example, we could go around like this and come back to 1, and then maybe I meander around a little bit on more of a graph, and then I eventually come back. But again, I have left 1, I've come back to 1, I've left it again, and I've come back to it. So it's always going to have an even count to the degree of a vertex. So that observation seems to be true in general, not just for this graph, but for any graph with an Euler circuit. Maybe this observation can be proved in reverse. In other words, maybe we can show that if every vertex has even degree in a graph, then that's enough to imply there's an Euler circuit. So this is the direction we are really interested in. I'm going to temporarily draw it in. It's going to disappear in a second, but that's the one I have a question mark over or under. If every vertex is even degree, does the graph have an Euler circuit? Be really nice if it did, because that would be a really simple check for whether a graph has an Euler circuit or not. We just have to look at the degrees of all the vertices, see if they're all even. It turns out that that exactly is the case, that a graph has an Euler circuit if and only if every vertex has even degree. And in order to get to that result, we're going to have to prove a lemma first. So we're going to prove this lemma, and then we're going to prove the main theorem of this lecture, which is Euler's theorem, which says that an Euler circuit exists if and only if every vertex has even degree. So let's start with this lemma, however. What does this lemma say? Well, it says, suppose you have a multigraph which has at least one edge. Then, if every vertex in that graph has degree at least 2, then the graph must contain a cycle. I want to start with the idea of the proof first, just to emphasize the fact that when we're asked to prove something, it's not like we're just going to immediately go down and start writing out the formal proof, full sentence structure, and the like. We got to brainstorm a little bit. How are we going to prove this? What ideas are we going to have to involve in this proof? And so oftentimes we brainstorm, sketch out, draw some pictures, get a feel for what's going on, the statement of the lemma in this case, the conclusion, and then how to go about proving it. So I've left a little bit of a gap here to sketch the idea of our proof, and then we'll go and formally write it up below. So what is the idea of our proof? We're going to use an extremal proof. So this is our technique we're going to go with. And what is an extremal proof? It just says get greedy. It says take the biggest thing possible, whatever that thing is that you're interested in, and see what happens. So in this case, I'm trying to show that the graph contains a cycle. Now, because I know there's at least one edge, and every vertex has degree at least 2, what I'm going to do is I'm going to say, well, there's at least one edge, so I'm just going to take the longest path possible in the graph. I'm going to start at a vertex and take the longest path possible. That's this idea of an extremal proof. Get greedy, take the biggest thing possible. And then let's see what happens. So take the longest path starting at vertex, let's say V0. So pick some vertex in the graph, take the longest path starting. So we're just getting a feel for what's going on here in our proof. Okay, so we're going to get our path. It'll look something like this. And it ends at some vertex. Okay, so that's the longest one possible. We can't extend it anymore. So what does that mean? Well, that means there's not going to be another vertex out here that I can connect it to. That's not going to happen. But we do know that every vertex has degree at least 2. So if I look at this last vertex, even though I can't extend this to a longer path, I know there's an edge hanging off of that, or another edge, I should say, hanging off of that vertex. So I know there's this other edge that comes out of it. And the question is, what does that edge have to do? Well, there's many possibilities. In fact, there's 3 sort of separate possibilities. That edge could go off and form a loop and come back. That's one possibility. We could get a loop. What's another possibility? Well, that edge could just come back to the previous vertex. In other words, I get a parallel edge. Those are 2 possibilities. And lastly, we could get that edge just comes back and connects to a previous vertex that we've already visited in our path. That's option 3. Note the option I'm avoiding is that that edge goes out and connects to a new vertex. That can't happen because this is the longest path that we have starting at V0. So there's no way to extend it to a longer one. So it's just that case can't happen. So we're into one of these three cases. And that means we're done because we've got a cycle. Either this loop is the cycle we were looking for, or these two parallel edges, just bouncing back and forth on them, gives us our cycle we were looking for, or this blue edge gives us a cycle we were looking for. And so we've got the idea of our proof all laid out here. Start with a vertex, take the longest path. We've got multiple cases that can happen. All of them lead to a cycle existing though. Either a loop, a couple of parallel edges, so a cycle of length 1, or a cycle of length 2, or a cycle of length 3 or more. And so that's the idea, is in any case, we get a cycle. Okay, so that's the essence of the idea of our proof. Now we're going to unpack it and write it all out. So here we go for our proof. We're going to let V0 be a vertex in G, and let P be a maximal path starting at V0. So in other words, P is a path that cannot be extended to a longer path. So we can draw what that path P looks like. Here's our picture. So we've got V0, say V1, and so on, out to, let's say, Vm minus 1, and then Vm. Since degree of Vm, that last vertex, is greater than or equal to 2, then there must be another edge incident with Vm. Let's call it E. So we'll call that edge E. Since P is maximal, so our path is of maximum length, then E must be incident with a vertex in the collection of vertices we already have in our path. So V0, V1, all the way up to Vm. So that's the other vertex it must be incident with. It starts at Vm and it's got to end at one of these vertices. So what we'll do is we'll let V sub k be the other vertex E is incident with. So in other words, what we mean is E is the edge Vm to Vk. Then what we have is three cases to consider. So we have three cases to consider. What are those cases? Well, case 1 is Vk is just Vm itself. Case 2 is Vk is just the prior vertex, Vm minus 1. And the third case is Vk, has k less than or equal to m minus 2. That's just a way of saying, hey, it's not Vk is not Vm, it's not Vm minus 1, it's something prior to those two. So let's draw these cases. So the first case is we've got Vm minus 1 and then Vm, and now we can draw this edge E in. E's a loop. because what we have is that our edge E is Vm to Vk, but in this case, Vk is just Vm. So in other words, it starts and it ends at the same spot. So this gives us a cycle of length 1. What's case 2? Case 2 is that we have our path P and our last edge, Vm minus 1. Maybe I should have labeled our edge. That was E. Our edge E in this case just went back to the previous one. So in this case, we have a cycle of length 2. And lastly, our third case, this was when the other vertex at the end of E was something earlier than Vm or Vm minus 1. So we're in a situation like this, Vm, Vm minus 1, and there's some vertex somewhere back down the line, let's call it Vk. So it went down, or it went back like that. Then we get a cycle as well. We have a cycle of length bigger than or equal to 3 in this case. And so our cycle in this case would be this thing here that I'm indicating in yellow. So in all 3 cases, we get a cycle. And that's what our conclusion is. Therefore, in any case, we get a cycle in G. And so there's our proof. It basically contained everything we did in that one line of our little brainstorming session, but here we elaborated on all aspects of it. You might say, is this important? Well, a very succinct answer to that would be absolutely, because, if I was to just focus on this part here, one thing that's never mentioned is the fact that we used the degree of V is greater than or equal to 2. I didn't write that anywhere in here. And so this is an incomplete proof because it doesn't look like it used all of the assumptions. Whereas I mentioned, here that those various 3 cases come up, but it's not clear even just looking at this diagram that I'm actually using 3 cases. It looks like I'm doing everything all at once. So this was a brainstorming session. It had some of the essential elements of our proof, but it did require us to go and unpack and write our formal proof out, get all those ingredients, bring them all together, break it up into the cases so it's very clear what's happening in each case and why we are concluding a cycle exists. All right, so that gives us our lemma that we're going to build off of. So again, just in short, this lemma says that if we have a graph with at least one edge and all the vertices have degree bigger than or equal to 2, then there has to be a cycle. Might not be clear why that's useful, but we're going to use it pretty much right off the start in our proof of Euler's theorem. So here's Euler's theorem. This is the characterization of a graph for when it has an Euler circuit. So we're going to start with a connected multigraph, and it's not the singleton vertex. So it's not just a single vertex with no edges. The reason we are excluding that case, so what does a singleton vertex look like as a graph? It would just be this. So I don't even know if you can see where I drew that, so I'll highlight it. This is that graph. It's a singleton vertex, no edges. Why am I excluding that case from this theorem? Well, because this theorem is going to say that an Euler circuit exists if and only if every vertex has even degree. Well, there's only one vertex. Its degree is 0. 0 is an even number. So yeah, every vertex in that graph has even degree. But it doesn't have an Euler circuit because our definition of a circuit says that it has to have at least one edge in it. And this doesn't have any edges. So that's just a trivial case that we have to get rid of. So that's what we're doing here is we're saying, let's exclude the singleton vertex. So I've got a connected multigraph. It's not the singleton vertex. And so from that, I have that it has an Euler circuit if and only if every vertex has even degree. That's what we want to prove. So let's go ahead and prove this. So because there's an if and only if in the theorem, there's two directions we have to prove. So I'll write down the first direction. That's this implication. If it has an Euler circuit, then every vertex has even degree. Well, this follows from our observation. That an Euler circuit uses two edges or a loop each time it visits a vertex. This adds a count of 2 to the vertex degree. And so the vertex degree must be even. So that's that direction. Now we'll go ahead and focus on the main direction we are interested in. And that is, if every vertex has even degree, then it must have an Euler circuit. We will prove this by induction on the size of the edge set. That's what we're going to do. We're going to prove it by induction on the size of the edge set. So let's start with our base case. And I'll say base case is, because we'll do it plural. So for the size of the edge set being 1 or 2, what do we have? Well, what can our graph look like? So it's connected, and let's say it's connected with one edge. What can it look like? If it's connected with one edge, it can look like this. Could it have two vertices? Well, if it had two vertices and one edge connecting them, then it wouldn't satisfy the hypothesis. The hypothesis says every vertex has to have even degree. In this example, the two vertices have odd degree. So in the case of having only one edge, we need it to contribute to the degree of a vertex as an even number, so it just has to be a loop. But we can have this situation with two vertices. It's just that in this case, we'd need two edges in order to make sure that they both had even degree. How else could we have two edges in a graph that's connected and every vertex has even degree? Well, we could have a single vertex with two loops on it. In each case, there is an Euler circuit. And I'll just abbreviate that by EC. So in each case, there's an Euler circuit. So now we'll go ahead and we'll write down our induction hypothesis. Assume the result is true. For all graphs satisfying the hypothesis, so that is every vertex has even degree, with the number of edges being bigger than or equal to 1 and less than n for n some number greater than or equal to 3. So that's our induction hypothesis. Assume it's true for all graphs with less than n edges, where n is some number greater than or equal to 3. And so then we're going to prove it's true for graphs with n edges. So now we're going to take it's going to take us to our inductive step. Let G be a graph with n edges and we got to also include our hypothesis here of the original hypothesis from the theorem we're trying to prove. And every vertex has even degree. And I guess we should include everything. And G is connected. So now, before I get into the rest of the proof, I'd like to instead just go to an example. So I'm going to leave a bunch of space here, but we will go down to an example. So an example of the method in the proof. So I'm going to test out our idea. I haven't told you what our idea is yet, but I'm going to test it out in a particular example, a concrete example, to get a feel for what we're doing, and then we'll write it up as a formal proof in general. So for this example, we should have a graph in mind. So I'm just going to quickly sketch out a graph. Okay, so I wanted to make the graph, sufficiently complicated enough so we can't just quickly eyeball what a Euler circuit is, but also not too terribly difficult. So the main idea with this graph is that I really built it off of a cycle. So there's this cycle. This is the one I actually built it off of, but if you look at the graph, you'll see there's many cycles all over the place in it. You can find cycles of length 2, length 3, length 4, and so on. I just happen to pick this cycle of length 5. And so what we're going to do is we're going to show how we can build an Euler circuit in this graph. One thing I want you to just observe is that every vertex in the graph has even degree. So that has degree 2, this has degree 4, this has degree 2, this has degree 4, this one has degree 4, and so on. And you just go around and check all the vertices. You'll see they all have even degree. So now I want to build an Euler circuit in this. I want to show one exists. How can I do that? Well, the way I can do it is I can start with this cycle that I've identified in the graph. I'll call that C. And now once I've identified that cycle, what I'm going to do is I'm going to remove the edges on that cycle. So just so we keep the original graph, I am going to just copy and paste it down here. So there's our copied version of our graph. And now I'm going to remove those edges on that cycle. I'll dash them in just so we know that they were sort of lurking there in the background. But I'm going to remove those edges. Now once I've removed those edges, what I do is I actually just split the graph up into a bunch of components. What are the components? Well, let's see if we can just color code them here. So there I've got my 3 components. I'll identify the vertices that were on that original C as to which component they belong to. And then lastly for this green one as well. So there we go. We've got our 3 components that we've just split our graph into. Took our original graph, found a cycle on it, removed all the edges on the cycle, kept the vertices, but removed all the edges. That split the graph down into a bunch of components. The main thing to realize with these components is that each one of them is a graph, a connected graph, because it's a connected component. So each one of them is a connected graph, which has every vertex of even degree. Why is that? Well, when I remove the edges on the cycle, all I do is I drop the degree of a vertex that's on the cycle by 2. Every other vertex in the graph retains its same degree, but all the ones that were on the cycle had their degree dropped by 2. And so if it originally had an even degree, then taking 2 away, still an even number. So every vertex in this graph still has even degree. The individual components are connected. So I can use the induction hypothesis that says, hey, there's an Euler circuit in each one of these components. So then what we do is we just find those Euler circuits in each component. So we go ahead and take that, maybe the green component up here, and I find an Euler circuit. So I'll go up, across, and then down this edge, around here, and then back to where we started. So there's an Euler circuit that started at, I'll call that vertex V1, and ended at vertex V1 and covered the whole of that component. Same with for this blue component. I can start at this vertex, maybe I'll call it V3 because it's sort of the third one around the cycle. And I can go around that component and get back to where I started. So there's an Euler circuit. And I can do the same thing for this purple component. I can find an Euler circuit on it. Now it's still a bit of a challenge to find the Euler circuit, right? You might make a wrong turn and get back to where you started too early and you haven't covered all the edges, so you just backtrack and see if you can find an Euler circuit. But the idea is we've reduced the bigger problem to a bunch of smaller problems. Kind of a recursive construction happening here. If you wanted to find, if you still couldn't find it in that purple portion, you could do the same kind of argument. Find a cycle in there, remove the edges, split them up, and do a recursive argument that way. But here we managed to be able to eyeball the Euler circuit on that smaller one. And now the idea is once we've got those smaller Euler circuits, we can stitch them all together. Of this again, and we'll paste it. And maybe I'll make a couple of notes here so we can find Euler circuits in each component. And then in this one, in this diagram over here, we will stitch the Euler circuits together. And so how are we going to do that? Well, now I'm going to look at my cycle. And again, I'm going to start at V1. I'll use well, actually, maybe I'll use the highlighter, the pointer. So I'm going to start at V1, and I'm going to go around the Euler circuit on it, get back to V1, and then go around the cycle until I get to a vertex that's in a component that I haven't considered yet. Here I am. I'm now at V3. Now I can go around its Euler circuit, get back to V3, and then continue around the cycle till I get to a vertex that's in a new component. There's one. I can go around its. Can't remember exactly which direction I went in, but here we go. We'll do another one. There's the Euler circuit in that one. Back to where we started, and then continue around. Oh, I'm at a vertex that I've already dealt with the component for, so I just keep going, and I'm back to where I started. And that's an Euler circuit for the whole graph. Now I'll just fill it in. So starting at this one, we go around the green component, and then around the cycle till we hit a new vertex, then around that component, around the cycle till we hit a new vertex, around this component till we, and then back to where we started, and then we get to a new vertex. Oh, that one's already part of a cycle that, or a circuit that we've dealt with, and we keep going around the cycle until we get back to where we started, and we've got our Euler circuit. So this is the idea that we are going to describe in our proof. Find a cycle, remove the edges, look at the components, use the induction hypothesis to find the Euler circuits on the components, then stitch them all together with that cycle, that sort of linking all of these components together. So that's what we're going to do. This is the kind of picture you should have in mind while we're doing our write-up for our proof. And I will warn you, this is going to be a long write-up because we have to describe that entire process. So the first thing we had to start with was that cycle. So we've got by lemma 6.2.1 G has a cycle. So that was the lemma that said if every vertex has degree at least 2, then there has to be a cycle. So our cycle is going to look like V1, V2, V3, V4, and so on all the way around. Maybe we'll call this Vm. Something like this. That's our cycle C. So we can let V1, V2, all the way up to Vm be the vertices on the cycle C. If C contains all edges in G, then we're done. Because it is a cycle that contains all the edges in the graph. A cycle is, by definition, also a circuit. Cycles are specific kinds of circuits. And so what we have found is then an Euler circuit. So if C contains all edges in G, we are done. We've found an Euler circuit. So assume it doesn't. So assume there are edges, just has to be at least one, edges in G not on the cycle C. Remove all edges, I'll say on C, from G to get a subgraph, which we'll call K, to get a subgraph called K. So we remove all of those edges. So I'm going to draw a picture again. It's like the one we had down below, but I'm going to try to make it a little bit more arbitrary. So we have this cycle V1, V2, V3, V4, and so on, Vm. And we're essentially removing these edges now, all these edges on that cycle. Now what could our graph look like? So this was all of C. What could our graph look like? Well, there'll be stuff hanging off of each of these vertices perhaps. And so I'm just going to kind of draw some arbitrary stuff. Once we get these edges removed and get our graph K, then we've got, you know, some things that maybe look something like this hanging off those ones, and then who knows, stuff like this, and then maybe some more stuff hanging off of that one. It could connect to other ones. We could even get some like V4, which just doesn't have anything else hanging off of it. It was just a part of the cycle and that was it. There was no other edges connecting to it. So this is what I'm thinking of. We remove all of the edges on our cycle C from our graph, and then that just basically our graph kind of falls apart. It's all the stuff that's still connected that form these connected components. So we remove all the edges and we get our subgraph K. K still has the property that all vertices have even degree, but K may not be connected. However, each component of K is connected. So by the induction hypothesis, each component has an Euler circuit, or is an isolated vertex. So in terms of our picture over here, once we've removed those edges, we get these components. So here's a component, we'll call that K1. Here's another component, we can call that K2. There's another component here, we'll call that K3. This component just consists of an isolated vertex. And we just keep going around. We get this component here, that's K sub, let's say K sub L. So we get all of these components when we remove the edges from C. Each of these components has vertices of even degree. They are connected because they are the connected components, and therefore they each have an Euler circuit, or they could possibly be an isolated vertex. So for all of the ones that aren't isolated vertices, they have Euler circuits, and that's by the induction hypothesis. And it's worth noting these Euler circuits contain a vertex on C. Might be kind of obvious based on our picture, but it's worth noting because we're going to need to use that fact that all these components, they have a vertex on C. And so now this sort of is our stitching point, where we're going to say find the Euler circuits on each of the components, and then we stitch them together with that circuit C. So now we can describe that stitching process that we did. So we start at vertex V1, and we travel around the Euler circuit until we return to V1. Then we travel around the cycle C until we hit a vertex in a new component of K. Let's say that new component is K2. Then we travel around the Euler circuit of K2. We continue in this way until we return to V1. This process must finish. So this process must complete or must finish since G is finite. There's only finitely many edges, finitely many vertices. So this process has to be complete. So in other words, just to summarize this last paragraph in terms of the picture, it says start at V1, go around the Euler circuit, return to V1, now go around the cycle. Oh, I've already considered the component that V2 is in. It's that component K1. Keep going. Oh, V3, that's in a new component. Go around its Euler circuit. Come back to V3, go around the cycle. Now I'm at V4. It's an isolated vertex. There's nowhere for me to go other than just to continue on my merry way past. Next vertex and so on. And we just continue on our way. Keep going around. Whenever we get it to a new component, it's either an isolated vertex, in which case we don't have to do anything, or we hit something that isn't isolated and we go around its Euler circuit. And then we get back to where we started and we found our Euler circuit. So this process must finish since G is finite, and therefore G has an Euler circuit. And so if I scroll back up to see, what part of the proof am I in? This is why I kind of color-coded these things. So the base case was written in yellow, then the induction hypothesis, and then we have our inductive step in white. So I'm still in the inductive step. And now we're out of the inductive step, and that'll be our conclusion. Therefore, by induction, so we're now out of the inductive step, we have just proven that the base case is true if we assume the induction hypothesis for that is true for all graphs with fewer than n vertices. We've now just proven it's true also for graphs with n vertices. So by induction, the statement is true for all graphs G satisfying the hypothesis. And so that marks the end of our proof. So arguably this is probably one of the longest proofs we have in this course. But there it is, all written out. So what have we proven again? Just to recap, we've proven that for a connected graph, which is not the singleton vertex, it has an Euler circuit if and only if every vertex has even degree. And not only have we proven that result, by our proof, we actually have produced a recursive algorithm for finding an Euler circuit. And that's what our example down here. So I wanted to make sure we did the example before the proof, because oftentimes, proofs can start to lead you to believe that, hey, maybe I don't really understand what's going on. So I wanted to do the example first to solidify these ideas. And then the proof was just the example written up in a formal way. But if we go back to our example, the way we did it was we said, find a cycle in there, which we did. That was that 5 cycle. Remove it, and then just find Euler circuits in each of the pieces. So we did our Euler circuits, and then we stitched them together. Now, when we look at one of these pieces, we may say, hey, okay, I need to know how to find an Euler circuit in a smaller piece. But we can do the same thing there. We could find a cycle in here, maybe that triangle, and then go ahead and remove the edges on that and find the cycles on the components that result when I remove them. So there's a recursive algorithm actually here for finding Euler circuits. So that's actually quite neat as well. Let's go back and revisit our motivating problem. So scroll all the way back up to the beginning. Our question was, is it possible to walk around the city of Königsberg and cross each bridge exactly once? So that's a question of, is there an Euler circuit in this graph? Armed with that theorem that says an Euler circuit exists if and only if every vertex has even degree. What can we say about this now? Is there an Euler circuit? And the answer is no. Odd degree, that's degree 3. Odd degree, odd degree, odd degree. In fact, every vertex has odd degree, so it's quite far from having an Euler circuit in some sense. So the answer is no. So now we come to the question of an Euler trail. Maybe asking for an Euler circuit is too greedy, starting and ending at the same spot. Maybe we're just interested in a weaker condition. Can we start at one place, cross every edge exactly once, and end somewhere else? Maybe not necessarily where we started. That's the question of having an Euler trail. I start at some vertex and I end at a different one. Is that possible? And so we can look at an example. We'll draw a quick example up here. Maybe something that looks like this. And let's see. Yeah, we'll let that be our example. I want to know, is there an Euler trail in this one, and can we find it? Well, I'll start at this vertex, and I'll just run through my list. So I'll cross that one first, so go along one, and then along this edge, and then maybe along this edge, and then around the loop, and then I'll cross this edge, and then this edge, and then maybe I'll go along this edge, and then along 8, and then along 9, and then along 10, and that gets me to here. So I started here, and I ended here. And I've listed in order the edges I've encountered as I crossed them. And so yes, we have an Euler trail. So yes, there is an Euler trail in this graph. Now, you may have tried to find one yourself. In fact, if you didn't already, go ahead and try to find some other Euler trails. One thing, though, I'm gonna warn you on is that I was successful based on the fact that I started at a vertex with a particular property. I didn't just start at any vertex. If you look at the vertex I started at, it was a vertex of odd degree. And look at the vertex I ended at. It had odd degree. Every other vertex in the graph had even degree. And that's necessary because if you think about what I'm doing, I'm going around, actually I shouldn't go on that one, I'll go along 6. I'm going around my graph, so I come into this vertex here along one edge, I leave on another one, I come in on another one, and I leave on another one. If this vertex down here is not one I'm starting at or ending at, it has to have even degree by the same reason before. We have to come in along one and leave along another. But for the one that I start at, it's going to have an odd degree because I'm going to leave along an edge, and then if I ever come back to it, I have to pass through it. So I have to contribute an even count. So I've got one edge that I leave on, and then I revisit it in pairs. And since I don't come back to it at the end, it's got to have an odd degree. And same with my ending vertex, has to have an odd degree. So this tells me that if I have a hope of finding an Euler trail, well, there's got to be 2 vertices of odd degree. Everything else has to be even. And that's our corollary listed down below. Corollary 6.2.3. A connected multigraph has an Euler trail if and only if there are exactly 2 vertices of odd degree. And we'd have to start at one and end at the other. I've left the proof as an exercise, but I will indicate very quickly how we could prove this using Euler's theorem. And that is, if I look at my graph up here, if I just add this extra edge in, so I add that extra edge, now my graph is all the green edges plus that one yellow edge. Now this is a graph with all even degree vertices, therefore there is an Euler circuit in it. So I could draw my Euler circuit on it. Once I've drawn my Euler circuit on it, I let that edge disappear, and I'm left with an Euler trail. And so that's how we could prove it. It's left as an exercise, but that's the idea. That's the fundamental idea. And what you'll find is a lot of times in graph theory, the idea you can see. It's getting that written up in a formal way. So that's why I've emphasized the getting or brainstorming the idea first and then writing up the proof in these two theorems that we've proven in this lecture. I will leave to you a couple of puzzles to ponder. There's 3 graphs there. Which of the following graphs have Euler circuits? Which ones have Euler trails? And when you think about in terms of an Euler circuit or an Euler trail, I'll scroll back up again. You can think of it as in terms of the question of, can I draw the graph with one stroke? So in this case, I can draw this graph with one stroke. I will actually do it right here. So I'm drawing the graph. Oops, I went around the triangle backwards. Then I labeled it, but regardless, there's another way to do it. So there's drawing the graph in one stroke. So if it's got an Euler circuit or an Euler trail, we can say, well, we can draw it in one stroke. So if you find that in these graphs, one of them, say, doesn't have an Euler circuit or an Euler trail, that means you can't draw it in one stroke. So then I've asked the follow-up question, what is the minimum number of strokes that you would need in order to draw the graph? All right, so that's it for this section. Thanks very much for watching, and we'll see you again next time.